有请基普索恩教授。Welcome, Kip S. Thorne.
Our universe has a warped side. By this I mean it contains objects and phenomena that are made from warped space and time instead of from matter like you and me and everything we see around us. Examples are black holes, gravitational waves, the Big Bang in which our universe was born, and perhaps also wormholes and time travel. I've had a 62-year career exploring this warped side of our universe, especially black holes. Black holes are made from warped space and time. For example, the circumference around this black hole is much smaller than its diameter. How is that possible? I'll explain using an analogy. Imagine a sheet of rubber supported by 4 tall sticks. Place a rock at its center so the rubber bends down. Then pretend you're an ant, a blind ant, so the rubber sheet is the only universe you know. You walk around the dashed blue circle at the top, measuring its circumference. Then you measure its diameter by walking down around the rock and back up the circle. The diameter is far larger than the circumference because your universe, the rubber sheet, is warped. Now, this same picture describes a 2-dimensional surface through a black hole's equator. I just changed the labels. Now it is the black hole space, the space of our own universe, that is warped. Our space is warped in a higher dimensional space that physicists call the bulk. And the rock is replaced by a singularity, to which I will return later. A black hole has a surface, which we call its horizon. Suppose I fall into the hole, transmitting information to you with a microwave antenna. Then inside the horizon, the hole's gravitational pull is so strong that nothing can escape it. I and my microwave signals are pulled inevitably downward toward the vicious singularity at the center. Now, not only is space warped inside a black hole, time is also warped. Time slows to a halt at the horizon compared to the flow of time back here on Earth, and inside the horizon, amazingly, time flows downward toward the singularity. That's another reason that nothing can climb out from inside a black hole. Nothing can move backward against the forward flow of time. Now, just as the Earth spins around its axis, so also almost all black holes spin, and that spin drags space around the black hole into a whirling motion like air in a tornado, fast near the hole's horizon, more slowly farther away. This is a precise picture of the warped space-time around a fast-spinning black hole. The colors depict the slowing of time. For example, at the yellow strip, time flows at 10% of the rate far away. And the whirl of space has an angular velocity proportional to the length of the white arrows, fast near the horizon and slow far away. If my wife, Carol Lee, is directly above a black hole's north pole, then her feet are dragged into whirling motion faster than her head. So her head sees her feet twist counterclockwise, and her feet see her head twist counterclockwise. This is similar to wringing water out of a wet towel. So there's a counterclockwise vortex of twisting space sticking out of the horizon's north pole, and similarly, a clockwise vortex of twisting space sticking out of its south pole. Now, in addition to vortices, there are also objects called tendices that stick out of black holes. I'll explain these in the familiar venue of the ocean tides on Earth produced by the moon's gravity. The face of the Earth nearest the moon feels a stronger gravitational pull than the far face, as shown by the arrows. And on the Earth's sides, there's a slight inward pull. The Earth's center doesn't feel the moon's gravity at all since the Earth is falling freely. So from the Earth's viewpoint, there's a gravitational stretching toward and away from the moon and squeezing from the sides. These produce our ocean tides. There's an alternative viewpoint that we have learned from Einstein's relativity. The stretching is produced by a stretching tendex, shown here in red, that reaches out from the moon and passes through the Earth, and the squeezing is produced by a squeezing tendex, shown in blue, that encircles the Earth. Similarly, a black hole has tendencies that stretch and squeeze everything near the hole, planets, spacecraft, or people, and these tendencies, like the vortices, are made from warped space-time. So what is a black hole? I'll describe what a black hole is by an extract from a recent book of my poetry and of paintings by Leah Halloran.
It's the sum of all its parts. Its space that is warped, the funnel of bulk being seas, its vortices of whirling space, its tendencies that stretch and squeeze, its slowing time and down cascading time, its horizon and its singularities, all made from warped space-time.
Leah Halloran's and my book will be published in China in February, and it's the most complete and most up-to-date place to go learn about the warped side of our universe. Let's turn from black holes to gravitational waves produced, for example, when two black holes collide. Einstein, in 1916, predicted and described gravitational waves. If the waves are propagating into the screen, then they consist of red tendencies that stretch everything horizontally and blue tendencies that squeeze everything vertically. And the stretch and the squeeze oscillate like this. We can think of space itself as stretching and squeezing along with everything in it. Because these waves are made from warped space, they're an ideal tool for exploring the warped side of our universe. The laws of physics tell us that there are only two types of waves that can be created in the distant universe and travel to Earth, bringing us information about their sources. Electromagnetic waves, including light, radio waves, X-rays, gamma rays, and more, and gravitational waves, which, like electromagnetic, have an enormous range of wavelengths. 400 years ago, Galileo built a small optical telescope. He pointed it at Jupiter, and he discovered Jupiter's 4 largest moons, and thereby he created instrument-based electromagnetic astronomy. In the subsequent 400 years, electromagnetic astronomy has revolutionized our understanding of the universe. In 1972, my colleagues and I began to develop a vision for the gravitational wave astronomy that would result if gravitational waves can be detected, and for the revolution that gravitational and electromagnetic waves together might produce. In that same year, 1972, my friend Ray Weiss at MIT invented the type of gravitational wave detector that would ultimately succeed. 4 mirrors hang from overhead supports, 2 along each arm of an L. A gravitational wave stretches 2 mirrors apart while squeezing the other 2 together, then the stretch and the squeeze oscillate. A laser beam monitors the stretch and squeeze by a technique called laser interferometry. However, the technological challenge was enormous. If the mirrors on each arm are separated by 4 kilometers, as they ultimately would be, then the strongest waves we could conceive, those from colliding black holes, would stretch and squeeze the arms by an amount 10 million times smaller than the atoms of which the mirrors were made, and 10 million times smaller than our best 1972 technology could measure. Our ultimate success 43 years later would require big science. More than 1,000 physicists and engineers from 15 nations, all working together in a collaboration superbly organized and managed by Barry Barish and others. The collaboration would have to invent, develop, and perfect new technologies at a total cost of about $1 billion US. And success would also require highly accurate computer simulations of colliding black holes. Now, to simulate colliding black holes by solving Einstein's equations on a supercomputer was itself an enormous challenge. Success required the invention and development of advanced computer technology, and it required a 55-year collaboration between experts on warped space-time and experts in computational science to develop the concepts and the algorithms for the simulations. This was a mixture of small-scale science and medium-scale science, again, carefully managed. And it required budgets of several million US dollars per year in the later years. But what we have learned from these simulations is marvelous. It has been a tipping point in our understanding of black holes and gravitational waves. Here we see the warped space-time of the first black hole collision that LIGO observed. This is from a simulation by the SXS collaboration led by Saul Tucholsky and headquartered at Caltech and Cornell. The two funnels are the two black holes as seen from the bulk, and the colors show the slowing of time, very slow where red, and downflowing time in the black region inside the hole's horizons. We've slowed the motion in order to watch the extreme distortion of space, like the surface of the ocean in a storm, and we pause the motion in order to watch the black holes collide, and then we watch the merged black hole oscillate as a burst of gravitational waves travels out into the universe. But as remarkable as this movie may be, it doesn't reveal how the waves are produced. There are two types of gravitational waves from colliding black holes. The first is generated by tendencies that stick out of the hole's horizons. When the orbiting holes collide and merge, their combined horizon, shaped like a dumbbell, tumbles end over end, and the tendencies attached to it sweep outward and backward like water from a turning sprinkler, becoming gravitational waves. The second set of waves is generated by four vortices of twisting space, two attached to one black hole and two to the other. As the merged horizons tumble, the vortices sweep outward and backward, and just as a moving magnetic field generates electric forces, so each outward sweeping vortex generates around itself stretching and squeezing tendencies, which become gravitational waves. These two sets of gravitational waves were created by colliding black holes 1.3 billion years ago in a galaxy far, far away. The waves flew out of their galaxy in which the black holes lived into intergalactic space. For 1.3 billion years, they traveled across the great reaches of intergalactic space until 50,000 years ago, when our ancestors were sharing the Earth with the Neanderthals. The waves reached the outer edge of our Milky Way galaxy. They plunged into our galaxy, and on 14 September of 2015, they arrived at Earth near the tip of the Antarctic Peninsula. Traveling upward through the Earth unscathed, they emerged at one LIGO gravitational wave detector in Livingston, Louisiana, and then 7 milliseconds later, they emerged from Earth at LIGO's second gravitational wave detector in Hanford, Washington. They stretched and they squeezed each detector's arms by 1/10,000,000th the size of an atom. And that stretch and the squeeze were monitored by the interferometric method that LIGO's director, David Reitze, describes in the following brief movie.
LIGO uses a device known as an interferometer to measure the tiny displacements in space. In this simplified representation, a laser beam is sent towards a partially reflecting mirror and split along two paths. The beams travel along the 4-kilometer arms and reflect back towards the central mirror, which recombines them, directing their light to a detector. As the gravitational waves pass, the distance between the central beam splitter and the end mirror stretches along one arm and compresses along the other. This changes the time it takes the light to travel along the arms. The recombined light waves shift with respect to one another and produce a signal at the detector. Incredibly tiny stretching and squeezing of space can actually be measured directly in this way. How little does space distort to make this signal? Let's zoom into a hydrogen atom until we reach the proton at its core. LIGO is so sensitive it can measure changes in distance as tiny as 1,000th the diameter of a proton. And this tiny measurement, made by LIGO, was the final step in a journey that began 1.3 billion years ago in the distant universe when two black holes collided.
The stretching and squeezing were analyzed with enormous care by a collaboration of 1,000 scientists and engineers from LIGO and from a project in Europe that had built a similar gravitational wave detector called Virgo that was not yet operating. After 5 months, this LIGO-Virgo team announced their discovery. By comparing with the predicted waves from the SXS team's computer simulations, they concluded that LIGO indeed had observed gravitational waves from two colliding black holes, and that the black holes weighed 29 and 36 times as much as our sun, for a total weight of 65 suns, and that the final merged black hole weighed just 62 suns, so it was as if 3 suns had been completely annihilated and turned into gravitational waves. The power output in gravitational waves during the brief collision was 50 times greater than the total power emitted in heat and light by all the stars in our universe put together. And the team deduced the distance the waves had traveled, 1.3 billion light years. This was a second tipping point in exploring our universe's warped side, the beginning of gravitational wave astronomy. The LIGO-Virgo collaboration has now observed more than 200 black hole collisions, and we're using our data to explore the laws that control black holes and the properties and populations of black holes in our universe. We've also observed several collisions of neutron stars, including one from which we're seeing every form of electromagnetic wave that astronomers are able to see. And we've observed several black holes swallowing neutron stars. We are exploring the warped side of our universe with gravitational waves. I shall now turn to a third tipping point, a radical and surprising discovery that the warped side of our universe and its material side are tightly connected by vacuum fluctuations. Now, what are vacuum fluctuations? Take a box and remove from it everything that possibly can be removed, so only a vacuum remains. The laws of quantum physics dictate that this vacuum must contain tiny fluctuations of everything that ever could reside inside the box, flashing in and out of existence randomly. For example, random fluctuations of light, of X-rays and gamma rays, and electrons, positrons, protons, and neutrons. Amazingly, these fluctuations contain no net energy and produce no gravity, except possibly exquisitely small amounts that I'll ignore in this particular lecture. Now, in 1973, the great Russian physicist Yakov Zeldovich alerted Stephen Hawking and me to the fact that vacuum fluctuations have voracious appetites. Whenever the fluctuations encounter any space that is rapidly shrinking or expanding or distorting, the fluctuations suck energy out of that changing space, converting themselves into particles of real matter. This triggered Hawking to discover that during its birth, a black hole transforms vacuum fluctuations into radiation that gradually leaks out of the hole's horizon for millions of years thereafter. We call this Hawking radiation today. And Zeldovich's insight triggered his young colleagues, Starobinsky, Linde, and Guth, to discover where all the matter and radiation in our universe probably came from. They speculated that our universe in its very early life expanded extremely rapidly, exponentially fast, and they called this inflation. And using the laws of physics, they showed that if our universe did inflate in this way, then vacuum fluctuations emerging from the Big Bang singularity sucked precisely the right amount of energy out of the inflating space to convert themselves into all the matter and all the radiation that we see filling our universe today. In this exploration of the universe's warp side, I now turn to wormholes and then to time travel. A wormhole is a hypothetical bridge across the bulk, connecting two different regions of our universe. For example, in the movie Interstellar, a wormhole connects our solar system to the core of a distant galaxy. Way back in 1962, my PhD mentor, John Wheeler, discovered that wormholes implode so rapidly that anything that tries to travel through them gets caught in the implosion and destroyed in singularities. This motivated several decades of study using the laws of physics. The tentative conclusions of these studies were these. Wormholes probably cannot form naturally in our universe, but they might be created by highly advanced civilizations. Such civilizations might hold wormholes open by placing exotic matter in their throats. By exotic matter, I mean matter with negative energy, whose gravity repels and thereby holds the wormhole open. This exotic matter might be made by modifying vacuum fluctuations. For example, if one region of the vacuum borrows fluctuations from another, the lending region will have negative energy and thus become exotic and repel gravitationally. But we don't know whether enough exotic matter can be made this way to hold a wormhole open. I suspect not, but my speculations have often been wrong in the past, embarrassingly often. Let's pretend that I and my wife, Carol Lee, are members of a highly advanced civilization, and we possess a wormhole. Then we might be able to turn the wormhole into a time machine. Carol Lee carries one mouth of the wormhole near a black hole where time flows very slowly, and she keeps it there for a year. I keep the other mouth far from the black hole, where I age by 30 years, while she ages by just 1. So looking through the space between us, Carol Lee sees me old. But looking through the wormhole, where we are holding hands, we age at the same rate, so Carol Lee sees me young. The wormhole has become a time machine. If I, an old man, travel through the wormhole from Carol Lee's wormhole mouth to mine, I'll meet my younger self. At the moment, so I'll just tell you that I wrote a technical paper on this, published in the famous journal of Physical Review Letters some years ago, and held my breath. And fortunately, my colleagues didn't criticize me too seriously for talking about this in a very, very serious manner, and we were very serious. At the moment the wormhole becomes a time machine, vacuum fluctuations will travel through it at the speed of light, returning to their starting point at the precise moment they left, thereby doubling their strength and acquiring positive energy. Traveling around the loop again, they quadruple their strength and so on exponentially. The result is a gigantic explosion discovered in 1990 by Stephen Hawking and me and our students using the laws of physics. Is this explosion strong enough to destroy the wormhole at the very moment it becomes a time machine? We don't know. It appeared to Hawking and me that the answer is controlled by the laws of quantum gravity, which no human understands at all well. But Hawking, who was never afraid to speculate, has formulated a chronology protection conjecture that every time machine that any advanced civilization tries to create will be destroyed by vacuum fluctuations at the very moment it is turned on, thereby keeping the universe safe for historians of all species. 62 years ago, when I embarked on exploring the warp side of our universe, it was a lonely effort. The warp side was thought to be more a subject for science fiction than for science, and I had only very few companions in that quest. Today, there are several thousand young scientists and engineers probing the warp side with gravitational waves, and hundreds probing it with computer simulations. And I invite you to join that quest. For example, go learn about the planned Chinese space-based gravitational wave detectors, Taichi and Tianqin. By the 2030s, or maybe 2050s, there will be a fourth great tipping point: the discovery of gravitational waves from our universe's Big Bang birth. The details of those primordial gravitational waves presumably are controlled by the laws of quantum gravity, which govern all singularities. So this tipping point may trigger a new quest, the quest to extract from the waves information about both our universe's birth and about those mysterious quantum gravity laws. Thank you.